Fundamental equations of dynamics. Okay, let's read it. Fundamental equation of dynamics is of a mass point. Newton's second law. Yeah, we don't care about that. We already know everything. Some equation expressed in the projections on the tangent and normal of points trajectory. Oh, okay. Wait, what? Are you serious? So it's for any points trajectory. It's not necessarily for. Oh, it's like capital R. Yeah, that actually. I mean, like this equation is just useless anyway, because unless you know what capital R is, you can't figure out anything, right? So only the first equation is useful. So yeah, and V tangential, come on. V tangential is the same thing as B because along the trajectory, it's always along the trajectory. So dV upon dt, it should just be the magnitude of V. So that times M, right? Yeah, that's equal to F. Makes sense, yes. I mean F tangential, of course. Yes, it does make sense. Okay, the equation of dynamics of a point in the non-inertial reference frame, k hat, which rotates with a constant angular velocity omega on an axis translating with acceleration omega naught. Okay, cool. Yeah, whatever. Non-inertial reference. Wait, what? Non-inertial reference frame? Are you serious? Okay, non-inertial reference frame. Which rotates with constant angular velocity omega about an axis translating with acceleration w naught. Oof, this is really weird. So, okay, so mass times acceleration. That is the what's F over here? And what's omega dash? Okay, I think omega dash is sorry, W dash is the acceleration uh with respect to the center of mass, right? Yeah. So fine. So force is equal to that plus m omega naught plus, and then there's this rotation stuff. So m omega r omega squared r negative makes sense, centimeter acceleration. Then you got this thing 2m. What's this? V dash omega. Okay. And what's this thing? V dash omega and a box around this. What does this even mean? I have no idea. Okay, whatever, next. So now we have questions. Let's do it. 59. An aerostat of mass m starts moving down with a constant acceleration. What's an aerostat? I don't know. Down with an acceleration of w. Determine the ballast mass to be dumped for the aerostat to reach an upward acceleration of the same magnitude. Air drag is to be neglected. What's an aerostat? I have never heard of this, so we'll ignore this. Yeah, okay, 60. In the arrangement of figure 1.9, the mass m0, m1, m2 of bodies are equal. So figure 1.9, cool. m1, m2, this is m0. The masses of the pulley and threads are negligible and there is no friction. The pulley, find the acceleration with which the body m0 comes down and the tension of the thread binding together bodies m1 and m2. Okay, if the coefficient of friction between the body, fine, it's no big deal. If the tension in this string is T, then you just have G minus T upon M0, which will be M basically because all of these are the same masses, right? Right? Yes. That's equal to, so the acceleration for this guys is T upon 2M. No big deal. So G is equal to 3 upon 2 T upon 2M. So 3T upon 2, right? So you just have T is equal to 2mg upon 3. So now we know what the tension is. We also know what the acceleration is, right? So the acceleration is this thing upon 2m. So your acceleration will just be equal to g upon 3. So these two are moving with g upon 3. So you can find out what force on m2 should be. There's just m2 g upon 3, which is like mg upon 3 basically. So mg upon 3 force has to put on it. So that's from the tension, of course. Coefficient of friction between, oh wait, what? There's coefficient of friction as well. Bodies in the horizontal surface is equal to K. Oh, you should have told me that. Okay, then this acceleration is slightly different. So this will be T upon 2m minus, so it's going to be what? 2m, I mean, both of these will be moving, right? Yeah, we want to find the acceleration with which the body m naught comes down. Yeah, so if these are going to be moving, we'll just assume that that is happening. So in that case, you can say, okay, what's the friction force on this? And it's only 2mg times mu. Coefficient of friction is k, I think, not mu, k. So k times g over here, because I don't want to. So yeah, this will be the new equation. So it's got g times of 1 plus k is equal to 3 upon 2 t upon m. So you got what the tension should be. So like t upon 2m, that is equal to, or just say t upon m, that's equal to 2/3 g into 1 plus k. So this thing, put that in there. So just g minus that. So g into 1 minus 2/3 minus 2/3 k. So it's going to be g upon 3 into 1 minus 2k. There we go. 60 done. G upon 3, 1 minus 2k. Alright, next question. But still it comes to the assumption that it is moving. What if it's not? Then maybe we should write a case-wise function for the acceleration. Nah, we just assume it's moving. Right. And yeah, I mean, this is obvious that if this is going to come down, then 1 minus 2k must be positive. So when k is equal to 1.2, I think when k is equal to 1.2, it will basically stop. Right. So that will be the critical condition. And then if it's bigger than that, then it won't go down, it will be 0. So you could write a case-wise definition for this, but hey, whatever. Next question. Two touching bars 1 and 2 are placed on an inclined plane forming an angle alpha with the horizontal 1.1, okay, 0.10, whatever. 1 and 2 are two touching bars, angle alpha with the horizontal. The masses of the bars are m1, m2, and the coefficient of friction between the inclined plane these bars are k1 and k2. So find the force of attraction of the bar in the process of motion. Minimum value of angle alpha at which the bars start to slide down. So we'll do B first. Or in fact, no, just go for A actually. Force of interaction of the bars. Oh, so like the normal force, I think. Process of motion. Fine, just write some equations. So if these are going to slide down, yeah, then what should happen is that, oh, and yeah, like what should happen is there must be a positive normal force. That is, these two must be touching at every moment. Only then A makes sense. If that's not gonna happen, then exactly, kind of. Oh, so they did say K1 is bigger than K2. Then of course these individually we just have two going faster down. Yes, these will be together all of the time. Let's do it. So what's the force of gravity on these things? Just m1 plus m2 g times sine theta, so sine alpha in this case, that is pulling it down. Okay, there's a retarding friction force, so minus m1 g cosine alpha times the coefficient of friction, which is, so they have k1 as the friction coefficient, minus m2 g cosine alpha k2, right? This thing is basically m1 plus m2 times acceleration. Cool, keep doing it. What we want is the force of attraction of the bars in the process of the motion. Oh, let's do B in that case first. So minimum value of angle alpha at which the bars start to slide down. So whenever A is 0, that will be a critical condition. So whenever A is bigger than or equal to 0, it will slide down. That's equal to, so that's a critical condition. Just have tan alpha is equal to m1 cosine alpha plus m2, sorry, m1 k1. There's no cosine alpha over there now anymore. Plus m2 k2 upon m1 plus m2. Right, and we want to know where of angle alpha. So tan inverse. Let's do B first. Okay, now let's do A. So you got the acceleration, right? Okay, cool. But okay, that's not sufficient. Let's think about each of these individually. So for the first guy, right, the equation of motion, they are both at the same acceleration. So, right, equations of the motion for the first guy, it will be m1 g sine alpha minus m2 g cosine alpha, sorry, m1 g cosine alpha k1 plus the normal force, that is equal to m1 times the acceleration, right? And then you got this thing, so you can just divide and get normal force, right? Or you could go for the other equation. So this will be m2 g sine alpha minus m2 g cosine alpha k1 whatever minus n is equal to m2a. I think this one is better, but yeah, who does even care about this? You just subtract it, right? Or we could do something better than this. Multiply this thing by m1, or maybe like divide by m1. So this will just be equal to g times sine alpha minus k1 cosine alpha, okay, plus normal upon m1 is equal to a, and then over here just have g into same thing, sine alpha minus 2 cosine alpha minus normal upon m2 is equal to a, and then subtract. That will give us a thing. So subtract means got n1 n upon m1 plus n upon m2 is equal to, so minus over there, but then that goes over top. So g, oh, this cancels, awesome. This is right, plus actually. So plus g times of k2 minus k1 cosine alpha is equal to 0. So just got n into 1 upon m1 plus 1 upon m2 is equal to g into k1 minus k2 cosine alpha, and k1 is bigger than k2, so this looks correct. N is equal to m1 m2 upon m1 plus m2 g into k1 minus k2 cosine alpha. This is oddly symmetric. I didn't expect it to be that nice looking, but we got it right. Okay, so there we go. A. Not interested in this thing, so it's just this value. Okay, let's go to 62 now. A small body was launched up an inclined plane set at an angle of 15 degrees against the horizontal. Did they give us any values? No. Okay. Find the coefficient of friction if the time of the ascent of the body is this much times the time of the descent. Oh yeah. Okay, I understand this. So it's moving. It's moving. That means kinetic friction. Right. So it's just going to be mg cosine alpha times I'm just going to use mu for coefficient of friction, right? This will be your friction, okay? And then you got, so while it's moving up, the thing is it's just mg into sine alpha minus cosine alpha times mu. That is our that thing is the force, so the acceleration is going to be this thing. So I should say deceleration, right? So this is equal to, and they look at time of descent or the, yeah, time of descent and ascent. Cool. So for time of ascent, call this thing, I don't know, dA. Yeah. What's the velocity change? Sorry, what am I doing? This should be upon T. What's the velocity change? They didn't give us what velocity it initially was or whatever. So just assume it's v. V upon T of ascent. And then for this guy, it's going to be G and Sine alpha plus cosine alpha mu. Wait, I think something's going wrong. Oh yeah, it's going wrong, definitely. There should be plus over here and negative over here. Because while ascent, both friction and gravity are acting with together. They are acting together to basically retard descent. When it's descending, friction is opposing the descent. So like this. V, the same thing. Wait, no, not the same. It's not gonna be V, is it? Oh, so what should we? Okay, okay, fine. That thing. Yes, we know how to do it. This times time of ascent squared. So half of that. So half AT squared. Oh, no, no. This is wrong. It should be UT minus all that stuff. Hey, but we can use VT minus half AT squared for this thing, right? So V is 0, then and then the acceleration is negative, and that's why it's going to be positive. So half of AT squared is still, right? So half of this magnitude of acceleration times t squared. That is still, it's just displacement, which we don't know. So call this thing t. And for this guy, it's going to be half and then time descent squared is equal to the same thing, so same t, right? Cool, but makes perfect sense. So divide this. So we just have time of descent squared, like mu squared. No, what was that? This quantity, okay, eta squared is equal to, so divide, you get that thing. Sine alpha plus cosine alpha mu upon sine alpha minus cosine alpha mu, which is basically just 1 plus tan alpha mu upon 1 minus tan alpha mu. Perfect. Right, this should make perfect sense. And from here you can figure out what mu should be, I think. Yeah. So multiply, just got this thing squared minus. This is weird, really. Wait, did I just? Okay, fine. Just squared time. What's this tan alpha? Sorry. Coefficient of friction is equal to 1 plus tan alpha coefficient of friction. So it's got coefficient of friction is equal to this thing squared minus 1 upon tan alpha into 1 plus coefficient of friction squared. That should do it. So this will be cot alpha into this quantity. So squared minus 1 squared plus 1. That should be it. Let's do it. So we are talking about 15 degrees right there. How do you figure out what cot alpha should be? I mean, this eta thing is not a big deal, but cot 15 degrees, that is big deal. Yeah. Yeah. Right, it's correct. The way I did it, that should have been correct, I think. Fine, so just find what cot 15 degrees should be. So 2 tan 15 degrees upon 1 plus tan squared of 15 degrees. That's a sine of 30 degrees, which is 1 upon 2. So it's got t squared minus 4t plus 1 is equal to 0. For cot, is still the same thing. So for cot is the same equation, right? So the roots of this thing are the same as roots of that. Minus c plus 4 is 15 degrees is going to be the lesser root. So it's going to be negative. That's b plus 1 square root of b squared. 16 minus 4ac upon 2a. It's going to be 2 minus square root of 4 minus 1, 3. Minus square root 3. That should do it. So cot alpha, that will just be 2 plus square root 3. Okay, don't erase this. 2 plus square root 3 times whatever this thing is, like 4 minus 1 upon 4 plus 1, so 3 fifths, right? Yeah. So 3 fifths of 2 plus square root 3. Next. So 63. Unless of course I'm making a mistake, which I think I may have made. But hey, whatever, next question. Following parameters of the arrangements of figure 1.11. There's 1.11. Don't see it anymore. Oh, this thing. Okay. Where did it go? 63, right? Are available. The angle alpha at which the inclined plane forms with the horizontal and the coefficient friction K between the bodies M and N. The inclined plane. Okay. The masses of the pulleys and the threads, as well as the friction in the pulley, are negligible. Cool. Assuming both bodies to be motionless at the initial moment, find the mass ratio M1, M2 upon M1, at which body M2. So, okay, for different conditions, if it goes down or goes up or it doesn't move. And yeah, find the mass ratio M2 upon M1. So, friction is fixed. Coefficient of friction is fixed, right? Right. So, there's coefficient of friction for this plane and this block. So let's analyze this guy's motion. What's the acceleration that M2 will go through? It's got what? G minus T upon M2. And yeah, like these are all frictionless, massless pulleys and strings. Works. Fixed inclined plane, I think. Yeah. That is equal to, so this thing is being pulled up. What's this? T upon M1 minus mu times G. I should use K times G. Of course, makes sense. Yeah, that is if M1 is moving. I mean, even if it's not moving, does it make a difference? Actually, it does. Then there's no friction. And there is still friction, but it's different. Fine. When it is moving, then it should be G cosine. Sorry. Did I by mistake? Did I take G anywhere else? Could it be? No. Okay, over here, it was satisfied first. No incline, right? That makes sense. So when it is moving, so for A and B, those cases, this will happen. Or in fact, no, let's just call this thing F. Yeah, the friction. So we'll assume the friction is constant. Fine. So it just becomes G plus F. And yeah, the friction force that is down the incline. That's what we are taking. So the sign is just like that. It's going to be T upon M1 plus T upon M2. And all of this stuff is just the acceleration for M2, right? So let's do it. T is equal to M1 plus M2. Wait, no, sorry. M1 M2 upon M1 plus M2 into, oh, this is bad. It's not the friction force. I think it's the frictional acceleration. So acceleration due to friction. Yeah, we'll just take it like that. Does it even make a difference? Just something. Something. Nice. And this times of what? G plus F. That's what T is. And what we need to figure out is what G minus T upon M2 is. So G minus T upon M2 will just be equal to M1 upon M1 plus M2 times G plus F. So this will be G times of I think M2, like M2 upon M1 plus M2 minus M1F upon M1 plus M2. So good thing is that M1F is now, it is the friction force itself, and M2G, okay, whatever. So there we go, M2G minus the frictional force upon M1 plus M2. That will be our acceleration. Nice. Okay, so now we have cases. So first case was what? 63rd, right? It starts coming down. So if it starts coming down, right, if M2 starts coming down, then M1 is going up. So like friction force is definitely just positive. So it's down the incline. Right. So for what mass ratio will this happen? So in that case, or in fact, just write it differently, right? We can kind of write it like, okay, whatever. Just call this thing M1 times F. That's it. That's it. Frictional acceleration. Nothing to worry about. Okay, cool. So I'm gonna write it like differently. Call M2 upon M1 as, I don't know, K. K we already used, so no, that can't be used anymore. X, yeah. So X times G minus F upon 1 plus x is equal to a, and like F max, the maximum magnitude of the frictional acceleration, that will just be equal to mu times g. Cool. Come on. So this will be x times g minus f is equal to a plus ax. And that will be x times of g minus a is equal to friction plus a. I get that. Okay, no, this minus a, that's equal to friction. Fine. So condition 1 is it starts going down. That is, the friction is it's positive and it's equal to mu times g, right? So condition A is this thing is just mu times g. That just means x times g minus a is equal to a plus g, whatever. Hey, wait a second. The minimum. Oh, right. So like acceleration should be. Okay. I understand what's happening. So yes, this is correct and all, but the actual thing is that in this case a should not be positive. That is the main criteria for this. Right. So you don't have to do this thing. Instead, you have to solve for a. Oh, that is. Okay, that's weird. So instead, you have to solve for a. So a into 1 plus x. Plus f is equal to x times g, or let's just go with it. Who knows? So 2xg minus f. That's the thing. So for this particular case, what you have is a into 1 plus x is equal to g times of x minus whatever k is, right? So yeah, perfect. So for acceleration to be positive, k must be less than x. Like x is bigger than k. That's the thing. So yeah, that is correct. And then the other thing. So for b, that is it's going up. The opposite should happen actually. Oh no, the whole condition is now different because now it's not positive anymore. It's negative. Yes. So now you just have a into 1 plus x, and yeah, like a should be negative as well. Is equal to g times of x plus k. Wait, what? This makes no sense. How can this be? Oh. This is correct, right? Yeah, it is correct. What? Starts going up, then acceleration is just negative. But okay, no, this is weird. This cannot happen. But if it is starting to go up, that's right. This is going down. Oh. Okay, I think I messed up the equation for. Right, I must have messed that up. Okay. I mean, like, look at this. M2G that's taken into account. Yes, friction is taken into account, but that gravitation force on M1, I think I didn't take that into account. Oh, come on. And I messed up everything. But I have to do it all of it again. I just hate this. Fine. So for M1, the friction we're considering to be downward, right? Just have M1 times G sine, right? So let's go with it. Oh, come on. P upon M1 minus, so it's supposed to be M1 G sine alpha upon that, so like minus G sine alpha. Okay, minus the frictional acceleration. That is our acceleration. Okay, cool. Upward acceleration, and for M2 the downward acceleration will be just G minus T upon M2. Should be nice. So it's got P into 1 upon M1 plus 1 upon M2 is equal to G into 1 plus, right, and I didn't take this into account. That's why everything went wrong. Fine, so like now we can do this T upon M. Let's go with T upon M2. So that will be M1 upon M1 plus M2 times all of this stuff. So now g minus that thing is going to be g into 1 minus of, so you got g into 1 plus sine alpha and then this times that. So 1, so like m1 upon m1 plus m2. And at this point, let's not use it. Let's use that notation that we have, 1 plus x, right? That is better. So it's going to be 1 plus sine alpha upon 1 plus. Now this is just getting complicated all of a sudden. You have this friction force right there. Minus, okay, what was I doing? Friction force upon 1 plus x. Cool. This is our acceleration. Now this should be doable. Okay, let's go with case number 1. Case number 1 is it is going downward. That means friction is positive and it's equal to mu times g. So it's gonna be, yeah, like acceleration should be positive as well. So whatever you get, that should be positive. So basically 1 minus of 1 plus sine alpha. So use s for this upon 1 plus x minus the coefficient of friction upon 1 plus x. That should be positive for it to go down. So what's the minimum? Minimum x value, but 1 plus x is positive anyway, so it just means like 1 plus x minus of, so you got 1 plus sine alpha. Come on. Oh yeah, so they have to multiply that anyway, so 1 cancels, okay, and then you got negative sine alpha right there, and then negative k greater than 0. So basically x is bigger than sine alpha plus k. It's that thing. Okay, cool. That's for a bigger than 0. For a less than 0, the opposite won't happen. Instead, you will have positive k right there, and that means it's gonna be x will be less than sine alpha, and and the opposite sign, of course. So here it was bigger than, then it will be less than, and this will be positive k instead. Makes sense? So it should be less than sine alpha minus k for it to go downwards, and wherever it's between that range, it's gonna be not doing anything. Exactly. Because in between that range, your friction will be, this magnitude will be less than what it can hold. So these are our two conditions. Just read all of this. So for A you have x is bigger than sine of alpha plus k. For B you have x is less than sine of alpha, the proper way, sine of alpha minus k. I mean, isn't this weird? Because yeah, it's dependent on alpha and everything, I get it. But what's saying, like, if the friction is like high enough, your x will be negative, which is impossible. So that would mean it actually never ever happens that it goes down if your friction is very big or if your sine alpha is very small. Cool, makes sense. C is, so if it doesn't do anything, so x belongs to this range. The other range, it's less than this and bigger than that. So wait a second. Sorry, interruption. Okay, next. This is a nice, collected result. Like, yeah. Next time I see a question like this, I'll just use this to actually figure out what is happening. No. Just do it the normal way. It's not useful at all. It's just a problem. 64th. Inclined plane of figure 1.1 forms an angle alpha is equal to, okay, without some issue. Okay. Coefficient of friction between the bodies M1 and M2 inclined plane is equal to K. Okay. The masses of the pulleys and threads are negligible. Find the magnitude and direction of the acceleration of the body M2 when the formerly stationary system of masses start moving. Come on. I just found out the acceleration. Now I just deleted the whole thing, right? Okay, calm down. Think about it. What was it? I don't remember. I just don't remember it anymore. Time to do it once again. Can't believe we have to do it so many times. I should have just written the acceleration like that. Why do it so many times, huh? Fine. What was it? So, okay, first of all, just had g minus t upon m2. That's equal to the one pulling it up, right? So it's like tension upon m1. And then the retarding forces, so minus friction force, so friction acceleration, sorry, and minus g sine alpha. That should be doing it. What's this happening? Okay, and then that just means t into 1 upon m2 plus 1 upon m1 is equal to all that stuff. Oof. Yeah, fine. Okay, this is equal to f plus g sine alpha plus g. What we need to find is just this thing upon m2. T upon m2 is equal to m1 upon m1 plus m, which is like 1 upon 1 plus k, sorry, 1 plus x of all this stuff, f plus g into 1 plus sine alpha and all that. Yeah. So this thing will just be equal to g into 1 minus of why is this so complicated? Okay, 1 minus of 1 plus sine alpha upon 1 plus x, and for this guy just minus frictional acceleration. Oh, okay, this is not g. It's minus the frictional acceleration upon 1 plus x, cool. Which is just, well, it's going to be x minus sine alpha. So g into x minus sine alpha minus the frictional acceleration, that upon, man, like f upon g, they should have a term for it. I don't know. It equals to plus minus coefficient of friction when it's moving, and it equals to something in between when it's not moving. They should really have a term for that. You know what? We could define a term like that. Hey, whatever, don't get ahead of us. Fine. 1 plus x. And even the term frictional acceleration, it's making no sense actually, but I still use it. Okay, this is the one acceleration. So 60. Yeah, I should just do this thing. Acceleration is equal to g times of x minus sine alpha minus the frictional force upon, sorry, frictional acceleration, of course, upon 1 plus x. So let's do it. Now what's happening in this case? 64th, right? Okay, so in this case they gave us the mass ratio, they also gave us the angle and everything. Okay, find magnitude direction, the acceleration. Fine, so you can use these conditions to figure out the direction first of all. So your x value, oh, so they are using this eta symbol. We'll use that eta symbol as well, in fact. So I mean, this looks like question of viscosity, but in different contexts it can be different. Anyway. Okay, so now we are at 264th. First of all, what's eta is 2/3. What is this quantity? K plus sine alpha. Square out K plus sine alpha. Coefficient of friction is 0.1 and sine alpha is just 1 upon 2, so it's 0.5. So that's 0.6, huh? So 2.3 is not bigger than 0.6, is it? Oh, it is actually. So 2/3 is in fact bigger than, yeah, like 0.6, because it's like 0.666, so on. So that makes sense. Yeah, it's gonna fall in the first category. So that just means that m2 is going to go down. So your friction force, it is positive. So friction acceleration is positive and it's equal to mu times of g. So in this case, your acceleration will just be equal to g times of this minus sine alpha minus. All right. This is okay, and downward for m2, which will be what, g times of, what's this thing? This is 2/3. This thing is 0.5, 0.1. So like 0.6, so 2/3 minus 6 upon 10, 2/3 minus 3 upon 5. And that thing upon 1 plus 2/3. It's to calculate this thing. So 10 minus 9, 1 upon 15, and that upon 5 upon 3. So send that here. It's like 1 upon 25, huh? That should be g upon 25. There we go. That's our answer. This is it. I'm gonna leave it like that because, yeah, they didn't tell us what g is supposed to do. Just gonna leave it like that. 64th. Yeah, skip all of this calculation. So g upon 25. Next question. 65th. A plank of mass m1 with bar of m2 placed on it lies on a smooth horizontal plane. What? They give us a figure? No, okay. Mass m1 with a bar of, okay, let's draw this thing. What? On a smooth inclined plane, right? No, horizontal plane. Plank, a bar on it. A horizontal force growing with time t is applied to the bar. Find how the acceleration of the plank W1 and of the bar W2 depends on it. If the coefficient of friction between plank and bar is equal to K, draw the approximate plots of it. Oh, come on. This is so, this is just tedious now. Okay, so this friction force AT on it, right? Find how the acceleration of the plank and of the bar W2 depends on T. Okay. So for small enough coefficient of frictions, small enough forces, they will both move together, I think. So it's a smooth horizontal plane, that's the thing. Huh? So okay, let's just figure out the dependence on the force F, because it's linear to time anyway. So when we draw the graph, we'll have to do it. Okay, so first of all, let's see. If this is moving together, then it's just F upon m1 plus. Yeah, it's that kind of problem where you have right. The okay problem is this bar, is it going to roll or not? What if it just slides and doesn't roll? Like, what am I supposed to do now? Wait, what? Bar of, so is this a cylindrical bar or something? Okay, you know what? Since they gave us the opportunity to take anything we want, I'm just going to take a box instead. Right, so it's like this is this kind of a bar, so it's cuboidal, very cuboidal. Right? This could also be correct, right? Why just go with cylindrical bars? So if it doesn't roll, that is, we can do it. So it's just this thing. This thing is m1, this thing is m2. Okay, cool. When these are going together, then F upon m1 plus m2, that's our acceleration. So that will be right. So this acceleration times m1, that will be the force applied. Right. So friction force applied on m1, and that is just m1. Okay, that friction force should be less than m1 coefficient of friction, which I think is k, times g. Makes sense. So this cancels. So yeah, fine. What we want is just acceleration. So okay, let's do it. W1. No. Both are same actually. So first case is when W1 is equal to W2 is equal to F upon M1 plus M2. So this happens till what? Till you eventually get F is less than, you know what? Like call this thing friction accel. We have been calling it that, right, all of the time. I use it very inconsistently, but for right now it's treated as acceleration. So then you don't need this thing. Times m1 plus m2. This should be good. Okay, and it's supposed to be f upon m1 plus m2, right? So let's figure out how the graph should be. Okay, not like that. This is how force changes, and this is how the acceleration changes. So let's go for W1 first of all. So for the first body, like okay, till this point both go together. So it's just equal to F upon m1 plus m2. Starts like that, I guess, and it keeps on going till you eventually get to this thing. So F is equal to kg m1 plus m2, and this thing is just F upon m1 plus m2 for both the bodies. Okay, and what happens after that when it becomes more than that? Then the other guy on the top. No, wait. The top guy is what is experiencing the force actually supplied through the top guy. So now what will happen is that because this friction force is falling short. I did it incorrectly. Hey, no, okay, fine, it's still okay. Because the thing is, what I did was I applied force F on the lower block. But it's still the same thing because it's smooth surface and everything, so it still works out. Friction force is still the same thing, it's just M1. Oh no. Okay, no. Something's wrong about this thing. Okay, the acceleration is just this thing, so this times of M2, that will be the friction force required. That should be less than or equal to M1 mu g. Uh-oh. So F should be less than or equal to M1 upon M2 times what we just found, kg. But yes, that's it. So this times M1 upon M2. Yes. I just want to put M1 and like M1 upon M2 as some kind of symbol. Whatever, just use M1 and M2. Okay, that's done. And now let's go to the next section where your force is slightly more. Just got accelerations are not the same anymore. So this lower block, it just experiences a friction force, complete friction force, right? So it's gonna be M1 G times K, that force, and that upon M2 is the acceleration. So for the second guy. And for the first guy, it will be F minus of this force, so M1 G times K, that upon M1. So that's gonna diverge. So for this guy, it's just F upon M1 minus G times K, right? So for this particular force, it was right. It would be like Gk times M1 plus M2 upon M2 minus Gk. So that would have been M1 upon M2 times, yeah. Something's just wrong about this, isn't it? Like the acceleration of the upper one just cancels out, and then you just got this minus that. So oh, come on, what would the acceleration have been? At this particular point, the acceleration would just have been m1 upon m2 times kg, right, for this graph, and same thing for this graph as well. So it's still okay. And now this thing, it has a slope and some negative quantity over there, whatever. It just goes like this, with a slope that is actually more than it should be. So like that. And this other guy is constant. So this thing is what, W1, that is equal to F minus G times K upon, sorry, F upon M1 minus G times K. And this thing is W2 is equal to, I'm going to use A1 and E2 because I like it like that. This will be what was that? This thing, right? M1 upon M2 times G times K. Yes. This graph really speaks up everything. It's actually a nice thing that we did this. You know, this graph could be used in so many ways. Even though it just has 2 sections, so might not be that useful. What if it had 3 or 5 sections? Then it would be super useful, right? Okay, no. Because figuring out which of these sections less, it's still just hectic, but it's kind of a nice thing. Okay, this is done. Let's go to 66th. Small body A starts sliding down from the top of, wow. Okay, where did it go? From the top of a wedge, figure 1.12. Okay, whose base is equal to 2.1 meter. Fine. The quotient of friction between the body and the wedge surface is given. What value of alpha will the time of okay, and what value of alpha will the time of sliding be least? What will be equal to? So what's the acceleration this guy receives? It's just going to be g times of sine alpha minus mu g cosine alpha, whatever, right? So you should just have the acceleration to be maximum. So what you want to do is, oh yeah, of course. Oh, okay, this is going down, so friction is opposing. Yes, it's opposing it. Body and the wedge surface is this. So K is constant, huh? Right. Figure it out. Suppose me G times of, so our acceleration has to be G times of sine alpha minus K cosine alpha. When will this be maximum? We ask. Yeah, this will be maximum when you have sine alpha is equal to K upon, no, it's not K, it's supposed to be 1, right? It's like 1, and then this is negative K. So 1 upon square root of 1 plus K squared. And cosine alpha is equal to negative K upon square root of 1 plus K squared. That should make sense, right? So cosine inverse of negative K upon square root of 1 plus K squared. That would be the thing. That's what alpha should be. Yes. And the magnitude of this acceleration is square root of 1 plus K squared times G. So this whole thing is just L is equal to half AT squared, half times of G square root of 1 plus K squared times T squared. So the time is, we can figure that out. At least you got when this will happen. So we can just put that in there. Call this thing alpha critical, I don't know. That will just be equal to cosine inverse of negative K upon square root of 1 plus K squared. That should work. Hey, wait a second. But why is this? Uh-oh. This is more than pi. Oh god, no. Oh, it's not nice. It's not nice. Look at this guy's derivative. That would just be equal to cosine alpha plus K sine alpha. It's always increasing. So the maximum acceleration, I mean, it's always increasing the first quadrant. So the maximum acceleration will be when alpha is equal to pi upon 2, which makes perfect sense. It will just go falling down, right? So where is it? What question was this? Wedge surface is K is equal to this, right? At what value of angle will the time of sliding be least? What will it be equal to? Come on, at angle alpha is equal to 90 degree, the time of sliding will be the least, but just 4. Oh, okay, this height, okay, this length changes, I think. Right. Fine. If this was not, like, okay, if this length was not changing, this would be perfect. This is changing. Fine. So you have to do it the normal way in that case. So acceleration, we got it. Our displacement, that will just be L upon cosine alpha. Our acceleration, that's just equal to G times of sine alpha minus K cosine alpha. Now we want to find a time. So S equal to half AT squared, whatever. It's like 2S upon A squared of that, that's our time. So 2 times of this guy. So 2L upon G. Oh, you gotta divide by A, sorry. Yeah, we are in fact doing that. So cosine alpha into sine alpha minus k cosine alpha. Cool. Square root of this thing, that's our time required. Now we just want to find when will be maximum. You know what? This is a nice general expression. I will keep it. I'll keep it over here. Who knows? They might ask you something similar. So 2L right there. Okay, that's there. The time required. Now, when will this time be the minimum? For that to happen, this quantity must be maximum. What is this quantity? It's just sine alpha cosine alpha minus k cosine squared alpha. So if I multiply by 2, right, maximizing the same thing as maximizing that, that will just be sine of 2 alpha minus, so 2 alpha goes from 0 to pi, perfect, minus k into 1 minus sine of 2 alpha. Hey, no, that's wrong. It's 1 plus cosine 2 alpha, sorry. So minus k cosine 2 alpha. And now this thing is maximum when 2 alpha is cosine inverse of negative k upon square root of 1 plus k square, which can happen. Exactly. So what do we have? We just have cosine of 2 alpha is equal to negative k upon square root of 1 plus k square. That's when this will happen, right? So it does ask this. What will be equal to? Yeah, so what will f of alpha will give this thing? So for this to happen, this should happen. This just means 2c square minus 1 is equal to all this stuff. Or, you know, you could just go with half of cosine inverse and all that stuff. That also makes sense. No big deal. Yeah, I like that better. That way we don't have to do all the calculation. So perfect. Oh, yeah, and gotta figure out what this is. So this will basically be 2 square root of L upon G, and then all of this stuff. So sine 2 alpha minus, okay, we need more space for this. Okay, minimize some stuff. Uh-oh. Okay, cool. This will be equal to 2 square root of L upon G into all of this. So sine 2 alpha minus k cosine 2 alpha minus k. That's what it should be. Nice. So it completely relies on 2 alpha and not alpha. Okay, this is a better thing in my opinion than this. Minimize. Cool. And we need to figure out what this is going to be. When. So yeah, like alpha critical is just half cosine inverse of k upon square root of k square plus 1. Negative k, sorry. So that means we don't need this anymore. And also not this thing. And in fact also not that. So now we can do this thing. So this has the maximum value as square root of k square plus 1. We want this to be maximum actually. So it should be square root of k square plus 1 and minus k. That will do it. That will do it, of course. Yeah. So t critical or t minimum or whatever, that will be 2 square root of L upon G into square root of k square plus 1 minus k. And actually, you know what, write it in a better format, right? It as L upon G times square root of k square plus 1 plus k. Exactly, multiplies by square root of k square plus 1 minus k. That will give us the thing that it was before. Now, is this a perfect square? Doesn't look like that. So that's it. We'll just have to leave it like that. So 66th turn. Okay. How much? Oh, quite a lot. We just started actually. 67th. a bar of mass m is pulled by the means of a thread up an inclined plane forming an angle alpha with the horizontal, figure 1.13. Where is the figure 1.13? So this is pulled up using a thread by an inclined plane forming an angle alpha with the horizontal. The coefficient of friction coefficient of friction is equal to k. Find the angle beta which the thread must form with the inclined plane for the tension of the thread to be at minimum. Oh yeah, sure. So it's not that bad as I thought it would be. What is it equal to? Fine. So this is not that bad. So it's just tension cosine beta is equal to, well, mg sine theta. Right. For wait. This has to be pulled up, right? Oh, uh, wait. If it has to be pulled up, then okay. This is just what acceleration. I mean, it depends on what acceleration it has, right? So the tension should be minimum. What if it's just about to be pulled up? What about that thing? This is weird. It's very vague. They didn't give us what acceleration it should have. Is it supposed to be at equilibrium, or is it supposed to be going with some kind of acceleration, or is it the critical condition where it just starts to go? Something like that. Come on, give us something. And I was thinking it was going to be easy, but really it's just a very badly framed question. That's it. That made it look like it's easy. It's not. Okay. We don't know the acceleration, so what assumptions do we go with? Okay, I will assume that it's at equilibrium, right? So when we say it's pulled up, maybe they mean, yeah, maybe they mean it's like at equilibrium. In reality, it's just not solvable because they didn't give us the whole condition. Tension should be minimum, so your acceleration could be the minimum, right? I mean, it's just barely existing, but it's upward. That could be the case. Okay, I'll just have to leave it because it's very vague. Okay, I'll just have to leave it this. So I won't be doing 67. Let's go to 68. At the moment d equal to 0, the force F is equal to 80 is applied to a small body of mass m resting on a smooth horizontal plane. Okay, the permanent direction of this force forms an angle alpha with the horizontal. Find the velocity of the body at the moment of its breaking off the plane. Oh, come on. Okay. Distance traveled. What I am interested in is the fact that this might just topple actually. Right? It could be possible. It just topples. Right? Oh, okay, it's not gonna pop. It's a smooth horizontal plane. That's a different scenario. Okay, so it's a smooth horizontal plane, huh? Fine. Then you don't even have to worry about what like it rotating or anything at some particular inclination. So it might be just inclined like this, right? It could be. We don't care about it, right? We just don't care about it. Because the thing is, it will be at equilibrium. That's all we need to know. And its mass is known and its acceleration is known. That's it. We don't need to know its position or anything. Right, cool. Yeah, that might be possible that it does SHM or something. But okay, we'll assume that doesn't happen. That really is not doable money. Okay, so let's do it. So what do we have? F sine alpha minus mg plus the normal force. Sorry, minus, no, yeah, like plus normal force. That is equal to 0 most of the times. But when F alpha will be more than mg, at that point it will break off. So for the breaking point, just have F critical is equal to mg cosec alpha. Okay, that's the vertical equation. What about the horizontal one? So it's F cosine alpha upon the mass. That's the acceleration. That's it. Huh? Yeah. So we'll have to do it like that. So okay, it's like its friction changes. Uh-oh. I think I messed up somewhere. Wait, there was a similar kind of condition over here as well. Where was it? Where we had to, where we had a time varying friction, right? Where did it go? I don't know. There was some question where we had a time varying, even, yeah, 65th. Right, F is equal to 80. It would vary like that. So okay, we just say that the plank is very large. If you would say that thing, yeah, sure, that might make sense. So our condition was something like, so initially it is going like this. That's what the acceleration is, and yeah, we just had to find what how it changed with, I mean, what acceleration was. That's all you need to know. The main question is, what about the relative velocity, right? Because if there's relative velocity already built up, then it will, yeah, it will just not, what am I saying? The friction will resist the motion, right? Anyway. So is there some condition that we are not taking into account? I mean, this thing is obvious. Okay. At different values of this friction, you have different things happening. And yeah, like this whole region, I don't have a worry about. As this looks correct. And over here in this whole region, as it's increasing, your relative velocity remains 0, 0, 0, and then suddenly boom. Now it cannot remain 0 anymore, and then it will have to break apart. Exactly, it still works. This graph is how it is, even though it's all happening in one go and not piecewise. But yes, it still works. So that's correct. What was it doing once again? 68, I think. Right. What do you want to find? Velocity of the body at the moment of its breaking off the plane. So once again, draw a graph so that you can do it. So our acceleration in the x direction, then we just do F cosine alpha, which is fixed, right, upon m, and our y acceleration, that will be 0 most of the time, but then after a certain point it will not be 0 when your n becomes 0, right? So try to graph this thing. We'll just go with yeah, like we can go with just x and y differently, I think. Velocity of the body at the moment of sleep. Okay, so we don't have to graph this actually. Just have a body up to this. Fine, no big deal. No big deal at all. So when it breaks off, there's no velocity in the y direction till now because it's just starting to accelerate. This x velocity over here, right? And that's this thing, F cosine alpha upon m, till the time, so till the force basically becomes this thing, right? Yeah. What time would that be? So force varies with time, right? Where was it? 48, 68, sorry. F is equal to 80, put that in there. So acceleration in the x direction, which is going to be a times t cosine alpha upon m, and then the t critical, that will be, so that's a right there, mg upon a cosec alpha, right? Cool. So displacement is just half a t square, so half times this quantity, 8, sorry, we cannot use that, sorry. Yeah, it's not doable. So first find the velocity. The velocity in x direction, that will just be equal to, hey, we just need to find the velocity. Oh, we also have to find distance. Fine, we can do that as well. So initially it's 0, I think. Okay, so critical velocity when it breaks off, that will be just putting this thing only. This is upon sine alpha. Lots and lots of calculation, I think. So a times this thing was like m squared g squared upon a squared sine squared alpha. You got this times 2m cosine alpha. Okay, m cancels, e and a cancels. Just got g squared upon 2a sine squared alpha cosine alpha. This is our critical velocity. Okay, find the displacement now. Use as for this. So that will be a t cube upon 6m cosine alpha, right? So at tc, what will this be? So that will be critical distance or displacement, whatever. Oh god, we have to put that in there. So there's some easy way to do it. A cosine alpha upon 6m, and then you got this times t critical is like m cube g cube upon a power 3 and then sine cube alpha, which will be m squared g squared upon 6a squared cosine alpha over there as well, and sine cube alpha. Wow, this is just horrible. Okay, why is this g squared, right? It should be g cube, sorry. A gets cancelled, m gets cancelled, so m squared, a squared, g cube cosine alpha sine cube alpha 6. Cool. So let's do it. The distance traveled till that moment, that is this thing, m cube g cube. What is this? Why is this so big though? Upon 6a squared sine cube alpha, and the critical velocity is this g squared cosine alpha upon 2a sine squared alpha. Cancel all of that. I accept this equation, still need it. So critical time is mg upon a sine alpha. This is so stupid. Oh god. Yeah, fine. That's it. This is our answers. So what we want is a velocity of the body moment of taking off, and this is traveling the body. So a is this thing and b is that thing. Let's line them up. This thing is a, this thing is b. Come on. And this is just some extra information. Okay, this thing is 68. 59. What time is it now? 2:40. I think it's more than 1 hour. We just do this. Just do it till 70 and I'll go. Bar of mass m resting on smooth horizontal plate starts moving due to force of constant magnitude. In the process of its accelerated motion. So horizontal plane, nice. The angle alpha between the direction of this force and the horizontal varies. Oh wow. This is even more. It's just the worst. Now the angle varies. Before the magnitude was varying, now the angle varies, where a is constant and s is the distance traveled by the bar from its initial position. Find the velocity of the bar as a function of the angle alpha. Angle alpha between the direction of this force and the horizontal varies as alpha is equal to as. So initially, s is the distance traveled, right? So initially it's 0. So yeah. What is the force analysis of this. Like there's this upward force. The maximum upward force could just be mg upon 3, which is, I mean, less than mg. That's all you need to know. The horizontal force will just be equal to mg upon 3. Actually, you know what? No, just gonna use f for this. So f cosine alpha, right? That upon m. That should do it. That will be the acceleration, and that's equal to basically d squared s upon dt squared. But then guess what? Alpha is just 8 times s. So f cosine of 8 times s upon m is equal to d squared s upon. Instead, we can write this acceleration as dv upon, so v dv actually, v dv upon ds. Cool. So it's got v squared upon 2. Initially, there is no, I mean, it's just starting, right? It's at rest initially. Fine. Resting on a smooth on. Yeah, cool. What we want is velocity of the bar is a function of the angle alpha. Doable, very much doable. So you got v squared upon 2 is equal to so since you just want alpha over there, what we can do is that instead of writing ds, we can just write das upon a. So this will be a times of this, and then you got das. So this is just alpha basically, right? Because yeah, sure. So now it will just be alpha right there. Makes sense, right? I think so. A is a constant. Sure. So it just becomes ab squared upon 2 is equal to f upon m, and then integration of this is the sine of alpha, and initially it's 0 anyway, so perfect. It's got v squared is equal to 2f upon ma times sine alpha, like that. So that's 69 for you, and that's what we need to find, right? Yeah, this is it. So 69th square root of 2f upon ma sine alpha. Cool. 70. Horizontal plane with coefficient of friction K supports two bodies, a bar and an electric motor with battery on a block. Huh? Is there a figure for this thing? No? Okay. Horizontal plane with a coefficient of friction K supports two bodies, a bar. What do they mean by a bar all the time? Is it a cylindrical bar? Is it a square? Come on. Just please don't do this kind of stuff. A bar and an electric motor with a battery on a block. So you have something like this, huh? A block on the top of it. There's a motor. I'm just gonna in case there's another block. So motor, fine, with a battery and everything over there. Okay. So that's just yeah, that's that. And there's a bar, which I just say it's another block, another body. That's all you need to know. Thread attached to the bar is wound on the shaft of the electric motor. Thread attached to the bar. There's a thread attached to this bar is wound on the shaft of the electric motor. Okay. The distance between the bar and the electric motor is equal to L. So okay, I'm starting to understand it. Like there's this movable pulley, something like that, right? There's a movable pulley like this, and on this pulley, you have a thread. So I say pulley, but it's supposed to be a motor. So makes sense, right? And then this is attached to another body. That's what we are saying. Distance between the bar and the electric motor is equal to L. So this length is L. When the motor is switched on, the bar, whose mass is twice as great as that of the other body, so this thing is 2m and this thing is m, starts moving with constant acceleration w. So all of this is on a smooth floor, huh? How soon will both the bodies collide? Hey, this is awesome. So it's very much doable. So acceleration is constant, it's just w. If this is moving with w, its force is 2mw. So the same force on this guy, that just means it's 2w. 2w is the acceleration of this body, right? So the d negative d square of what am I saying? Yes, negative d squared of L upon dt, right? So the acceleration, I mean, you could say relative acceleration or anything. Yes, so relative acceleration will be 3w exactly. So no problem. Half into 3w d squared. How soon will they collide? Easy. It's supposed to be 2L upon 3w square root of that. There we go. Square root of 2L upon 3w. Done. This wasn't that hard. Or maybe it's supposed to be done in some other way. Okay, fine. 70 done. So I'll see you guys in the next video. Bye.